One of the tools we used when we were dealing with circuits with lots of capacitors in them was series and parallel combinations and equivalent capacitances. So we could take a fairly complex circuit and pick out pieces that were in series and parallel and combine them into equivalent capacitors. And sometimes, not always, but sometimes we could work our way down to a single capacitor and then work our way backwards and figure out what the charge and the potential difference across every capacitor in this complicated circuit turned out to be. Well, we can do the same thing with resistors. We have rules for resistors in series and resistors in parallel, and we can use them the same way to deal with complicated circuits and simplify them, and use that same trick by working backwards and finding the current through every resistor and the potential difference across every resistor in a fairly complicated circuit. Here are my two circuits. I have 3 resistors in series on the circuit on the left, and 3 resistors in parallel in the circuit on the right. I know that for a series circuit, the current through every one of these resistors has to be the same. Whatever current comes into resistor 1 and out of resistor 1 has to go into resistor 2. And when it comes out of resistor 2, it has to go into resistor 3. There are no forks in the road. There are no branches in this circuit where it can take a different path. The current has to go from one to the other to the other. That's how we know they're in series. When I look at my parallel circuit, the current that comes out of the battery gets to a fork in the road, gets to a junction. We call that a junction, right here. And part of it can take a path to the other side through resistor 3. It's sort of like going to the supermarket, and you have your items and you're ready to check out, and you walk up to the check stands, and there's a whole bunch to choose from. And you're trying to get out of the store as fast as you can. And each one of those check stands is a resistance to you getting out of the store. And you look, and you only have a few items. So you say, oh, I'm going to go to the line where they limit to you to a few items. But there's already 6 people in that line. And then you look at the line next to it, and there's only 1 person there, but they've got a big basket full of stuff. And you have to decide. 1 person with a big basket full of stuff is a big resistance. But there's only 1 person there in front of you. The other line is a small resistance, the quick check line. But there's a bunch of people already there in front of you. And you have to decide. Well, the electrons do the same thing when they're moving through a circuit. They would like to take the path of least resistance to the other side. If R1 is the smallest resistor to the other side, and R2 and R3 are bigger, most of the electrons are going to take the path through R1. But eventually, it's kind of like that quick check lane at the supermarket. Eventually, so many people are there, you go, I'm going to go in the other line because it's going to be faster. That's what the electrons say. So many electrons are going through 1. Some of them decide to take path 2, even though there's more resistance there. They say, I'll get out of here quicker taking this path. And some will decide to take the path through resistor 3. As long as there is some resistance between every path, between point A and point B, some current will take every path. Now, if we put a 0 resistance path from A to B, that's called a short. And all the current will take the path of 0 resistance. And nothing will go through R1, R2, or R3. All the current will take the path of 0 resistance. That's called a short. And typically, that's a bad thing to have in your circuit. So we'll ignore that for now. And we'll look at the case when every path has a resistor in it, and some current takes every path. But we do know one thing. More current is going to go for the path with the smaller resistance. So if the current from the battery comes up and has a choice when it gets to junction A, and it can split, part of it can go this way, we'll call that I3, and part can go up this way. And when this current gets to this junction, part can go this way, we call that I2, and part will come this way, we'll call that I1. And when this current comes together again on the other side, what do we have over here? We have the current that we started with. So in this situation, we know I1 plus I2 plus I3 is I battery. They add up. Now let's take a look at the potential differences across each of these resistors. In the case of a parallel circuit, it's pretty straightforward. The potential difference across 1 and 2 and 3 are all the same and equal to the potential difference across the battery. In the series circuit, the potential differences add up. The potential difference across 1 plus 2 plus 3 add up to be the total potential difference across the battery. And we can work this out and figure out that our equivalent resistor, if we wanted to draw one resistor that was equivalent to these three in series, and it had hooked up to the same battery, would flow the same current, we would just add up the resistors. And if we were to do the same thing for these resistors in parallel, we would have to do it this way. 1 over R equivalent, 1 over R1, plus 1 over R2, and we can keep adding them here. The overall resistance, when you have a group of resistors in parallel, the total resistance is less than any one of them in the group. It's less than the smallest one in the group. And every time you add another resistor in parallel, you're reducing the overall resistance. I know that's a little weird to think about. You're adding a resistor, but you're reducing the resistance. It's because you're adding another path to the other side. Think about trying to get out of the supermarket. Each one of those check stands is a resistance to you getting. You can't just walk out the store. You got to stop, scan your stuff, pay for it, right? It's a resistance to you getting out of the store. But the more check stands that are open, the quicker you're going to get out of the store, the easier it's going to be for you to get out of the store. So the more resistors we have in parallel, the lower the overall resistance is. And as a quick reminder, let's recap what we got for capacitors in series and capacitors in parallel. For capacitors, the charge on every capacitor in series was the same, and the capacitance went down when we added them in series because the voltage was being split up over more and more capacitors, and they all had to have the same charge. In parallel, we added up the Q's, the charge, and got an equivalent capacitance that was the sum of all the capacitors in parallel. Let's do this example where we use our series and parallel rules for resistors to come up with one equivalent resistor for this circuit. What are you going to do first? Can you spot the section you're going to do first? These three resistors are in series. So for resistors in series, I can add them up. So I can replace those 3 resistors with this one right here. This is an equivalent circuit. Now, what do you spot next? Well, these 2 are in parallel. So for parallel resistors, I can use my rules for resistors in parallel, and I come up with 1 over C equivalent 2. 1 over 6 plus 1 over 6. I get C equivalent 2 is 3 ohms. So I can replace those 2 resistors, those 2 6 ohm resistors, with a single 3 ohm resistor. Now, it should be easy to see that these are in series. So we get an equivalent resistance of 6 ohms. That means that we could have a circuit with a single 6 ohm resistor that would flow the same current when hooked up to the same battery as this complicated circuit with 6 resistors.